So can we start?
Yes.
Yes.
Please.
Okay. So it's a big pleasure, personally and professionally, to have the honor of share this first European non-associative algebra seminar in this 2026. Uh, well, I welcome all colleagues working on non-associative algebras, and of course, it's a good moment to wish all of you a happy new year, peace, prosperity, and everything for this new 2026. So, after welcoming all of you here, I shall simply introduce the speaker today, who is Mateo Tomašević, who is coming from the renewed Zagreb school and is speaking on, sorry, it should be here. He is speaking on automatic additivity of multiplicative and Jordan multiplicative maps. So it's your turn. Thank you.
Thank you. Thank you very much for your introduction and for your nice wishes. I'll now share my screen. Okay, I hope you can see my slides.
Yes. It's perfect now.
Okay, great. So before I start, I would also like to thank Professor Ivan Kajgorod for the invitation to speak on this seminar. So this is actually based on a joint work with my former PhD mentor, Ilja Gogić. Ilja Gogić is probably here listening to me. I would also like to connect this lecture with his lecture he did on this very seminar about 2 months ago. So this is all based on our joint work, which can be described as attempting to characterize Jordan multiplicative maps via preserving properties, usually on matrix algebras and on other operator domains. In his lecture, he was talking about some different aspects of our work, but due to time constraints, he didn't get the time to mention this particular part, which should be actually a bit more accessible than what he was speaking about. He was speaking about some continuous spectrum shrinkers and so on, and this part is basically mostly algebraic. So I'm going to be talking about a classical problem in ring theory and abstract algebra, which can be formulated like this. So the problem of automatic additivity asks, so given two rings R and S, when is a multiplicative map from R to S automatically additive? So it should be understood as we should find some necessary sufficient conditions on the rings and on the class of maps which we consider, which will together enforce the automatic additivity of such maps, of course. So this multiplication can be standard, it can be associative, non-associative, and so on. There are many variants. So this problem is relatively old and has a rich history. It was first considered by Rickert, who actually connected this problem to the problem of unique multiplicativity or unique multiplicative structure of rings. So actually given a multiplicative structure on a ring, the question is whether this multiplicative structure uniquely determines the additive structure on the same ring in different settings. So this question was considered by Rickert and by Stevenson, and it was it can be reduced to this problem of automatic additivity for maps. First result I'm going to state is a classical result of Martindale, which says that every bijective multiplicative map from a prime ring, which is a ring which satisfies this condition, which contains a non-trivial idempotent onto an arbitrary ring, is necessarily additive and thus a ring isomorphism. So this kind of result is in some sense typical for this theory. It has the assumption of bijectivity along with multiplicativity. So very rarely do we get an automatic additivity result for all maps. Usually we have some assumptions such as bijectivity or some kind of non-degeneracy or injectivity or something like that. And this other part is, of course, a structural condition on the rings. Okay. Next result is more relevant for our considerations because it considers matrix domains. So it's by Jodeit and Lam. R is some principal ideal domain, and we consider maps from n times n matrices with entries in R to itself, which is assumed to be multiplicative, and it is assumed to be what the authors call non-degenerate, which means that the map is not identically zero on all singular matrices. Then the authors characterize the form of such maps. What we obtain is a first condition is some kind of a, let's say, trivial one, where there exists a non-zero idempotent such that the map phi minus p is multiplicative and degenerate. So basically phi equals a fixed idempotent up to a degenerate multiplicative map. And the second option is the additive variant, where this map phi is actually implemented by a conjugation via an invertible matrix T, composed with an entry-wise application of a ring endomorphism, and possibly composed with the map with the cofactor map. So it is a map which maps every matrix to its cofactor matrix, which is defined as a transpose of its adjoint matrix. So you take all n-1 order minors of a matrix, you put them in a matrix, and you get an additive map. So in this second option, we do get some kind of automatic additivity, and this first option is in some sense trivial, so this result is also typical in some sense. Okay. So the same question can be asked, and more information can be obtained in the case when that R is actually a field of characteristic 0. So the authors Yang and Zhu did the following classification of such multiplicative maps. It's a bit long, and there are many details, but the first option is this. So the first possibility for phi is that phi is up to a similarity equal to this block diagonal map, where the first block is another multiplicative map which goes from the field to a smaller matrix algebra, and this other part is some kind of a fixed idempotent. So basically this map is also in some sense what the authors I think call trivial, because it maps every singular matrix into a fixed idempotent up to which is diagonalized up to this similarity T. The second option is what we call in the previous slide degenerate maps. So these are maps which map every singular matrix to 0, and this is evident because they factor through a determinant of an additive map through a multiplicative map on the field. Here we have determinant of phi 1, and then everything is multiplied by phi 2, where maps phi 1 and phi 2 are precisely those described in the previous slide, those additive variants, so compositions of conjugations, the cofactor map, and an entry-wise application of a ring endomorphism. And finally, we get to a true, let's say, true additive option. It's the same on the previous slide, so a conjugation via an invertible matrix, an entry-wise application of ring endomorphism, and possibly a cofactor map. So it's not particularly necessary to remember everything here, but I just want to point out that this classification is a bit messy. There are still some parts which are, let's say, a bit undetermined, such as this, and there are many options, so we don't get automatic additivity for free, let's say. So, okay, this is particularly relevant for us because we will look at the similar problem on the matrix domains, and but we won't necessarily look at under the standard multiplication. We will look at some other types of multiplications, and therefore it is interesting to note that analogous problems for automatic additivity were considered, for example, for Lie multiplicative maps by the author Arjantsev. So this is actually a good introduction for the topic of Jordan multiplicative maps, which is what we will study today. So first I will introduce Jordan algebras. I mean, probably many people who listen to this seminar are well versed in Jordan theory. I'm going to just make a quick introduction. And Ilja also in his lecture 2 months ago did a similar overview. But I'm going to be brief now. So basically Jordan algebras, they're a class of non-associative algebras which are analogous to Lie algebras. They're introduced first in the context of quantum mechanics by Pascal Jordan. They're defined as, they can also be rings, of course. They're defined as non-associative rings of algebras whose multiplication satisfies the following two axioms. So we first have commutativity, which is in contrast to the anti-commutativity in the Lie case. And we have this, what we call Jordan identity, which is kind of a substitute for associativity, a weaker form of associativity, which guarantees that Jordan algebras are necessarily power associative. And Jordan homomorphisms are homomorphisms in the category of Jordan algebras. So these are linear or additive maps in the case of rings, which preserve this kind of a product between Jordan algebras. So this is going to be the topic for today. Of course, in the context of an associative ring or an algebra, we can naturally induce a Jordan structure by taking these kinds of products. So what we denote by diamond, X diamond Y, is this symmetric product. So it is similar to the commutator, which is used in Lie theory, but we have here plus instead of a minus. Also in the context where 1/2 can be defined, so if the ring is two torsion free or the algebra is over a field of characteristic node 2, this kind of a normalization is usually used, especially in physics, because here a regular product for commutative elements is actually equal to this circle product. So this is kind of nice. So, and moreover, in Lie theory, it is well known that every Lie algebra is actually induced as a substructure of an associative Lie algebra, where the Lie multiplication is given by the commutator. So we have this enveloping Lie algebra. A similar result is actually not true in the Jordan case. So there are Jordan algebras which do not arise as subalgebras of associative algebras, where the multiplication is defined this way. Those are called exceptional Jordan algebras. But in our considerations, and actually in most practically relevant applications, those kinds of Jordan algebras do not arise. So most of them are indeed are coming from associative contexts, and therefore, basically, the study of those Jordan algebras in most practically relevant cases boils down to associative algebra. And this is the context we will be working in. So Jordan homomorphisms can therefore be defined purely as objects in the context of associative algebras and rings. So between two associative algebras, we say that a linear map is a Jordan homomorphism if it preserves this operation. So this is that diamond product we have defined before. Of course, we can also put 1/2 in here. If the map is linear, it's the same. And when the rings or algebras are two torsion free, which means in the case of algebras that the field is of characteristic node 2, this condition, along with linearity, can be reduced to this, or rather is equivalent to this. So this simple property says that the map phi preserves squares or commutes with squares, and therefore it is well connected with the multiplicative structure of the initial algebra. So from here, actually, we also see what are some basic examples of Jordan homomorphisms. Those are multiplicative homomorphisms and anti-homomorphisms of rings or algebras. Of course, this is trivial because they automatically preserve squares and are linear. But there are many other examples. And in fact, the central problem, let's say, of Jordan theory is trying to describe in which context does every Jordan homomorphism, do we have the dichotomy of every Jordan homomorphism is either multiplicative or anti-multiplicative. It indeed is true in many contexts. Or failing that, can we in some other way describe the structure of Jordan homomorphisms through homomorphisms and anti-homomorphisms, rings or algebras? Okay, so in our context, we will in most cases have this dichotomy, but it's not a central question for us at the moment. So what we'll now look at is the problem of automatic additivity of Jordan multiplicative maps. So instead of the regular multiplication, now we will assume Jordan multiplication, preserving Jordan multiplication, and we will see whether this implies additivity for maps. So the first result of this type was obtained by Molnar, who started this area of research. So for a Banach space X, we denote by X prime is dual space, and we for an operator, for a bounded operator on X, we denote its Banach space adjoined by A prime. And we also introduced the concept of a standard operator algebra as a subalgebra of the algebra of all bounded operators on X, which contains all bounded finite rank operators. And the theorem states this: so if we have two Banach spaces. The first one is of dimension at least 2, and we have two standard operator algebras. Then we look at the map phi, which is assumed to be bijective between those two operator algebras, and it satisfies circle preserving property, which means that it's multiplicative with respect to the circle multiplication, which is defined like this on these algebras. Then we obtain the following result. So if Banach space X is assumed to be infinite dimensional, then phi assumes one of the following forms. So it can be a conjugation by an invertible bounded linear or antilinear operator, or basically the same type, but we also have a composition with the map which maps every operator to its Banach space adjoint. So these two first options are multiplicative maps. These second two are anti-multiplicative. In the final dimensional case, then, because of bijectivity of phi, we immediately obtain that the domain and codomain have the same dimensions, so we can assume that the phi actually maps is a map on the matrix algebra over C. Then we get this classification, then there exists an invertible matrix and a ring automorphism such that phi is implemented via conjugation by T and an entry-wise application of this ring automorphism, possibly composed with transposition. So this form is what is important, what we should remember moving on. And we immediately see the similarity of this form to that one form we obtained earlier for regular multiplicative maps, but there we had the cofactor map here instead of the transposition. And now we see basically those maps such as determinants, cofactor maps, and so on, they do not interplay well with the Jordan products, so we will not see them here. This kind of strange behavior is completely erased. We obtain these very simple forms of maps. And this form will be in some sense typical moving on. We will see this many times also in our results. Okay. I would also like to mention that the same conclusion holds for maps. It should be bold. The same conclusion holds for maps on this defined on the space of all self-adjoint bounded operators on some Hilbert space H. So the same. So it is a bijective map which is assumed to be circle multiplicative, and then we obtain the same conclusions. So this domain of self-adjoint bounded operators is actually interplays very well with the Jordan product because it is actually a Jordan algebra. Because if we have two self-adjoint operators x and y, then xy plus yx is again self-adjoint. And it is actually a prototype of a special Jordan algebra. So these results, which obtains an automatic additivity of bijective Jordan multiplicative maps between two general Jordan algebras. So this is not special. This is this definition. This goes from the definition of Jordan algebras, where A is assumed to possess an idempotent satisfying certain technical properties. So with some structural conditions on A, we do get an automatic additivity, and this kind of result actually encompasses all previously stated results. This is way more general. Okay. And also, we would also like to mention this result, which was actually pretty much an inspiration for what we did. So this is a result which considers again the algebras of all self-adjoint matrices, but in the finite dimensional case, so Hermitian or anything like that, so which are Jordan multiplicative in this sense. Then the authors obtain a full classification of these kinds of maps. So the first option is that phi is a constant and actually equal to a half of an idempotent, of Hermitian idempotent. And the second two options are the additive case, where phi actually is equal to a conjugation via a unitary matrix and the same possibly composed with transposition. Okay, and so finally we arrive to our result, which perhaps looks at the most natural example of a domain where we could look at this. So we look at the domain of M and F, so n times n matrices with entries in a field F, where F is assumed to be of characteristic different for 2, and n is assumed to be at least 2. And then we consider maps which are from M and F to itself, and we prove that all such maps that such a map is Jordan multiplicative, which means that it preserves this kind of circle product. We use the normalization with 1/2, if and only if phi is either constant, in which case it takes a fixed idempotent value, or phi is additive, and in which case phi is characterized like this. So it is either a conjugation via an inverted monomorphism and possibly composed with a transposition map. So again, we see this kind of a form appears what we saw in Moller's result, but for us we did not assume any kind of injectivity or bijectivity, which is also evident in the fact that these constant forms appear. So this kind of result is actually in the form very similar to this kind of a previous result, but here the authors did not have the normalization 1/2. I'll explain why the difference is made. So basically, also I would like to point out here some kind of a rigidity we get in the case of Jordan multiplicative maps. So if you recall, when we looked at multiplicative maps from MNF to MNF, we got this kind of many cases, which were some of them were a bit complicated. So we got determinants, we get cofactors, and so on. Here in the case of Jordan multiplicative maps, we have a certain rigidity. So phi is either constant or is automatically additive. So the classification is a bit simpler. Okay, so the next natural question, as I said, is to look at Jordan multiplicative maps with respect to two different kinds of products. So we introduced the diamond operator, which is this regular Jordan multiplication, and the circle operator, which denotes this normalized variant with 1/2. There is actually a simple relationship between, let's say, between maps which preserve one or the other in this sense. So if phi is a diamond multiplicative map, then psi defined by this simple transformation is easily shown to be circle multiplicative. So if we do have a result for, let's say, all circle multiplicative maps, then we obtain a result for all diamond multiplicative maps automatically in this context. So this theorem actually could be stated pretty much the same with the diamond operator here, but the only difference would be in the constant case. In the constant case, we would have 1/2 of an idempotent instead of an idempotent. So this kind of a maneuver can be actually made in many of the previously stated theorems, but the authors seemingly were not directly aware of this, because in some cases they stated two variants of each theorem, so one with 1/2, one with the other. Of course, it is, from the definition, it is not clear how to eliminate the 1/2 because you don't have any kind of homogeneity property, but again, using that maneuver, one can actually obtain both variants. Okay, so this settles the question. So of which multiplicative variant we will use. We did use circle because in this case it is simpler with respect to idempotence. We will get that this map phi automatically preserves idempotence. We will see. But before we go on, I would like to now discuss some counterexamples which state that this theorem cannot be verbatim extended to other domains and in other settings. So the first situation we can look at is what if instead of the full matrix algebra, we look at some subalgebra. So the prototype would be the algebra of upper triangular matrices. So in this case, the theorem fails in the sense that we can find examples of maps which are circle multiplicative, but are neither constant nor additive. So this rigidity, this dichotomy, fails in this setting. So as an example, we can look at this map, which takes an upper triangular matrix, erases the strict upper triangle, and on the diagonal applies some kind of a non-additive multiplicative map, such as the squaring map. And then this map is neither constant nor additive, but is circle multiplicative. And in this case, this is also a multiplicative map as well. Okay, the next kind of a possible generalization would be in the case of infinite dimensions. So if H is an infinite dimensional Hilbert space, then one can identify it with sum of itself. And then one can define this map, so which maps every every operator to a block diagonal operator, when on one block we have the operator itself, and on the other block we put a fixed non-zero idempotent. Then this map is easily seen to be circle-multiplicative, but it's neither constant nor additive. So again, the rigidity phenomenon fails. And a final consideration could be made in the case of fields of characteristic equal to 2. So in this case, of course, the circle multiplication is not defined. So circle multiplication has a normalization 1/2, but 1/2 is not well defined in the case of characteristic 2. But of course, we can look at diamond preserving maps and ask the same question. So whether the map is necessary we can consider this kind of a set. We can consider this kind of a set which starts from some arbitrary matrix and then iterates Jordan multiplication by arbitrary matrices on it. So we get a kind of a left-nested iterative Jordan product starting from, let's say, a seed matrix X, and we have to see what this set looks like. So this proposition says that if the starting matrix is not equal to 0, then this set is actually the entire matrix algebra. So this is interesting from a structural aspect because it reflects a crucial fact that the Jordan algebra M and F with the standard Jordan multiplication is a simple Jordan algebra, meaning that all Jordan ideals are trivial. And this set is in some sense an ideal, of course, without the linearity part, but it is circle absorbing in the sense that if we have a matrix which is inside this set and another matrix which is arbitrary, then its Jordan product is again guaranteed to be inside this set. So this proposition so says that Jordan algebra MNF is in some sense simple, but actually without the assumption of linearity, because this is of course not assumed to be a subspace. This part is crucial because it shows that it shows some kind of an, let's say, injectivity phenomenon for phi. So if for phi, because if phi annihilates some matrix, then iterating Jordan products by other matrices, we obtain any other matrix. So we get that phi is actually a zero map. So basically any matrix which is non-zero cannot be mapped to 0 in the case of non-trivial phi. Okay, regarding other elements of the proof, they boil down to operations on idempotence and the structure of idempotence. So in general, if A is an algebra, we can define two operations, two relations on idempotence. So this standard partial order idempotence and the relation of orthogonality. And then it is easy from the definition to see that any circle multiplicative map automatically preserves these operations in some sense. So we get the following properties, which are easy to show from the definition. And this is actually in a bit more general context between two matrix algebras of possibly different dimensions. We get that automatically phi preserves idempotence. We get that phi preserves the order of idempotence. And then with the assumption that phi is non-zero but maps 0 to 0, we actually obtain that phi also preserves orthogonality of idempotence and is a rank increasing map for idempotence. Moreover, if we assume that the codomain has the equal dimension to the domain, then we get even more information. So we actually get that phi is rank preserving. Then we get that phi preserves the orthogonal idempotent, which is defined like this. So the identity minus p. And we also get that the restriction of phi to the idempotence is an orthoadditive map, which means that if we had two orthogonal idempotents, then phi is actually acts as an additive map on them. And we get similar result actually, which is which extends the previous part to a linear combination of mutually orthogonal idempotents. So these are elements in the proof which follow a rather immediately from the definition, from the assumptions. Okay, so also this corollary is interesting to note. So if we have a Jodeit multiplicative map from a matrix algebra to a smaller matrix algebra, then it is necessarily constant and therefore equal to a fixed idempotent. So this explicitly eliminates all those examples such as determinants and such maps which were multiplicative in the case of M and F, let's say to F. In the case of multiplicative maps, so these kinds of maps are not viable in the Jodeit multiplicative case, which is to be expected. Okay. Then we move to a different setting. So I mentioned that our previous theorem cannot be readily extended to other matrix algebras, to subalgebras of the matrix algebra, but it can be done in the context with some other hypothesis extra. So I'm going to now introduce the concept of structural matrix algebras, which are basically the most natural examples of matrix algebras, which are defined like this. So given a quasi-order ρ on the set of all indices, it is defined to be a reflexive transitive binary relation. We define a structural matrix algebra, or an SMA, associated to ρ as a subalgebra of Mn spanned by the matrix units whose positions are precisely indicated by incidence with respect to the quasi-order ρ. So basically, we pick some positions and we take a linear span of those positions. So on those positions we can have any value, and on other positions the matrix entries has to be 0. And so when this kind of object is precise as subalgebra if and only if the set of positions is defined by a quasi-order. This one easily sees this, and of course this kind of an algebra is always unital. Moreover, Ilya have noticed that these subalgebras could be precisely characterized as those subalgebras which contain the algebra of all diagonal matrices. So we have a rather simple characterization. So these structural matrix algebras were many times considered in research. They were introduced by Van Wyk, and in fact I did my entire PhD thesis on structural matrix algebras and on characterizing Jodeit homomorphisms on structural matrix algebras. So this is a natural extension of that work. Before we state any results, I will just here define some structural concepts regarding these algebras, regarding the structure of such algebras. So first we begin with the description of a center of such algebra. So if you have a quasi-order, then we can define this kind of a triple tilde relation, where we say the two indices from 1 to n are related if and only if they're comparable with respect to the quasi-order ρ. And then we take a transitive closure of such relation, and then we obtain an equivalence relation. And the quotient set with respect to this equivalence relation consists of what we call central classes of the SMA A ρ. This definition, or rather this nomenclature, is useful because those central classes actually characterize the center of an SMA, which can be described as diagonal matrices which have equal entries on every central class of A ρ. So if two indices belong to the same class, then those particular diagonal entries have to be equal. So this is the full description of the center. In particular, we obtain that the dimension of the center E is equal to the cardinality of the quotient set Q. And moreover, we can actually decompose the entire SMA with respect to its center in a particularly nice way. So for any subset of indices, we define the corresponding diagonal idempotent like this. So it's a sum of all those diagonal matrix units with supports in this subset. And when we consider such idempotents for the set of indices C, where C goes over central classes, then we obtain a mutually orthogonal family of idempotents, which are easily seen to be the elements of center, and their sum is equal to the identity map, to the identity matrix. And then we therefore obtain and see that this family is actually a basis for the center of the SMA. And we can actually act with every such idempotent on the algebra itself to obtain a kind of a two-sided ideal, which has 0 rows and columns on all those rows and columns belonging to indices which do not belong to C. So by erasing those rows and columns, we actually obtain a smaller subalgebra, which is easily seen to be, again, an SMA. So not only a subalgebra, but again, an SMA in a smaller matrix algebra. And it is also a central SMA, which means that its center is trivial. So it consists only of scalar matrices. And moreover, we get an isomorphism. So the original large SMA is actually obtained as a direct sum of all those central smaller SMAs. And this fact is what we refer to as the central decomposition of A rho. So A rho is we were able to basically decompose it into a sum of some kind of atomic small indecomposable elements, which are these central SMAs. Okay, and now we arrive to our theorem, which uses this. So this is a theorem from a different paper, which was a continuation of our considerations on MNF. So here we have structural matrix algebra A rho defined in M and C, so over complex numbers. And we're looking at a map phi from A rho to M and C, which is assumed to be injective and is assumed to be multiplicative with respect to 3 different products. So first is the standard matrix multiplication. The second is the Jordan product diamond, and the third is the normal Jordan product. Then we obtain the following conditions. So the first one is a structural condition on the SMA itself, which says that all central classes have cardinality equal to 2, or more nicely, it can be characterized as that SMA does not contain a central or rank 1 idempotent. Okay, and this is equivalent to the fact that all such maps phi are additive. So we actually characterize exactly for which SMAs are all such maps additive. So by such maps, I mean multiplicative or Jordan multiplicative. And moreover, in this case, if this is the case, we also obtain a full description of such maps, which I state here. So this part actually is not that novel in the sense that I already in my PhD thesis described the form of all injective Jordan homomorphisms precisely. So once we do have an additive Jordan homomorphism, basically then it is known what is the form, but to obtain that it is additive, this was actually the hardest part, of course. So this is what they look like. They're implemented by a conjugation by an invertible matrix. Then we have an action of a transitive map, which I will describe below, and which acts on some kind of a sum, which goes over central classes, and on each central class it acts as a component-wise application of a ring endomorphism, possibly different for each central class, which acts on these central components. So these elements are belonging to those central summands of A rho. And then on each class we have a possible extra assignment, which is either the identity map, so it does nothing, or it can be transposition. So in this case we obtain we see the situation where the Jordan multiplicative map, or actually Jordan homomorphism, is not necessarily multiplicative or anti-multiplicative. So on one class we can have transposition, on another class we can have the identity, so it mixes both properties. But anyway, let me just describe. So what is this transitive map? So the novel element with SMAs is that not every automorphism is inner. So there are outer automorphisms which can be constructed like this. So we start with a map G, which is defined on the quasi-order, on the underlying quasi-order, and goes into non-zero complex numbers, which is assumed to have this cyclic index property. And then any such map can induces an automorphism of an SMA on the standard basis by mapping every matrix unit to a scalar times itself. Then this property is used to show that this is an automorphism, and indeed any description of any kind of Jordan maps or isomorphisms or so on will necessarily include these kinds of maps, because again they cannot be implemented by conjugation by some invertible matrix. So it has to be included here. Okay, so this is the theorem. And basically now we will move on to the final part of the talk, which will look at some different Jordan-like products. So there is actually another result we have shown, and this was very recently, as in a few weeks ago, which concerns multiplicative maps with respect to some kind of other product. So we have to get to this product. So if we have a Jordan algebra, we can define several different natural products on it. One of them is what we call a Jordan triple product, and is defined like this. So we take three elements and define this type of cyclic expression, which is actually very reminiscent to the Jacobi identity in Lie algebras, but in the Jacobi expression we will have plus here instead of a minus. Now we define it with a minus, and the difference is that this is not always zero. Actually, most times it isn't zero in the case of Jordan algebras. And this kind of a product is very well researched in Jordan theory. In the case of special Jordan algebras, which means that we have an enveloping associative algebra with respect to some kind of multiplication, then this kind of a triple product reduces to this nice formula. So it is 1/2 of ABC plus CBA. So this kind of symmetric triple product. Okay. A key special case is obtained if you plug A equal to C. Then we obtain what is sometimes called the Jordan semi-triple product. So it is a triple product of ABA. Then we obtain this kind of expression, which looks complicated. But again, in the associative case, we obtain a very nice identity. So the triple product of ABA equals ABA, where this is an associative multiplication of the enveloping algebra for the Jordan algebra. Okay, and this kind of a product was very well researched in the context of Jordan homomorphisms, because we have some of these equivalences. So if you have a linear map between two Jordan algebras or some field with characteristic not 2, then this kind of a map is Jordan multiplicative. If it is Jordan multiplicative, then it necessarily preserves the Jordan triple product and the Jordan semi-triple product. And we also have a converse if, for example, the map is assumed to be unital. So it maps, so if the algebras are unital and phi maps unity of the first algebra to the unity of the second algebra, then we have the converse implication. So if we have a map which preserves these products, then it is necessarily a Jordan homomorphism. So basically, it makes sense to look at preservers of these products and expect to obtain a Jordan homomorphism or close to it. And indeed, this was done in many research papers. So here we consider several results which looked at Jordan semi-triple product preservers. So again, we have Molnar, which looked at we have a similar result to the one for Jordan multiplicative maps, which says this. So if we have two Banach spaces, the first one is of dimension at least 3, and we have again two standard operator algebras. And if you have a bijective map which preserved the Jordan semi-triple product, then we obtain that phi is a plus-minus ring anti-automorphism. So this part is actually exactly the same form as what we had in Molnar's previous theorem. So that conjugation via an invertible linear or antilinear bounded map, and possibly composed with the map which takes an operator maps it to its Banach space adjoint. But the novelty element is here, this plus minus. We can also have minus such maps. Okay, so we basically do get again automatic additivity, but the form of such maps is we can also have negative such maps. Okay, so a similar result is also reproduced by An Hu, also same authors as before, which considered the Jordan multiplicative maps in the context of bounded self-adjoint operators on a Hilbert space, again, such a result exactly this in this form, which with this plus minus is obtained in this case. Also, it is interesting to note this result again in the context of matrix algebras, which is most interesting to us. Here, where the authors looked at injective maps between two matrix algebras, which satisfy this, so which are assumed to preserve the Jordan semi-triple product. And then the authors obtained that phi is plus minus a ring anti-monomorphism, which of course again attains this very well-known form with again a constant plus or minus 1. So the novelty here is that this is injective, so it is not again assumed to be bijective, but the authors made away with subjectivity. Okay, now we will attempt to motivate a product which we have considered. So if you have a Jordan algebra, then usually one can consider a quadratic multiplication operator, which considers this symmetric. This is the Jordan semi-triple product. So for a fixed a and the variable x, this is what we obtain, and we see this expression a squared circle x. This a squared is of course a circle a with respect to this multiplication in the Jordan algebra, and this expression is actually equal to the again Jordan triple product of ax. So again everything is connected. So this kind of a product is what we will look at, and this kind of product actually has other uses. So in the context of JB algebras, so these are Jordan algebras with a submultiplicative norm, which are assumed to be Banach algebras and satisfy an extra identity, then this kind of a product is used to define orthogonality in such algebras. So the author Battaglia defined two elements to be orthogonal if this product is 0. And therefore, it makes also sense to look at preservers of this kind of product, and this was actually also done by the authors Gorbanipur and Hejazian. So they looked at a real standard operator algebra, Jordan operator algebra. Those are defined to be Jordan subalgebras of the Jordan algebra of all self-adjoint bounded linear maps on a Hilbert space, which contain all bounded finite rank operators. So this is kind of a Jordan analog of the standard operator algebra, and they looked at maps which are assumed to be bijective between by bijection on one Jordan operator algebra, which preserves this kind of a product, so this kind of a squaring variant. And then the authors obtained that phi is equal to epsilon times psi, where epsilon is plus or minus 1 and psi is an automorphism on A. So basically, I think this should be a Jordan automorphism, of course, because yeah. So basically, we do get again an automatic additivity result and a structural result again with this plus minus Jordan homomorphism, which is to be expected. So okay, if in the particular case where A is the full algebra of all self-adjoint maps, then we obtain plus minus anti-unitary conjugation. So this is that form which we saw before in result by Forstner and Kuzma, but again it can also have a minus sign. Okay, this was all motivation for our result, which is actually in its preprint form. So we did this a few weeks ago. So here we have F is now an algebraic closed field of characteristic not 2, and we look at these kinds of maps. So maps on M and F to itself, which satisfy what we call the mixed Jordan power identity. So it is this kind of a product, but K is now some fixed integer, so it's not necessarily 2. We generalize it to any K. Then we obtained this kind of a classification. Such a map is either constant, and it takes a fixed K+1 potent value. I will explain what it is. And or phi is necessarily additive, and moreover, the form of such maps is epsilon, so some root of unity epsilon, kth root of unity, times well-known form, so conjugation by invertible matrix, and the composition with an entry-wise application of ring monomorphism omega, possibly composed with transposition. So basically the standard form, but now it is multiplied by a kth root of unity epsilon, which actually fits nicely into those cases we saw before where we had plus minus for k equal to 2. So this is actually what you do obtain in general. So of course we started with k equal to 2, and then we saw that the methods could be generalized to n k. Here we have this k plus 1 potent. Now on this slide I will explain what it is. So if A is an algebra over F, then we say that an element P is a k potent if kth power is equal to P. So if k equals to 2, of course we get idempotence, and any idempotent is necessarily a k potent for all larger k's. And moreover, this set of k potents has a structure which is very similar to the structure of idempotence. In particular, we can define two relations, which we saw earlier. So an orthogonality relation defined like this, and the partial order relation, which is defined like this. So this is actually exactly the same definition as in the case of idempotence, where in the case of idempotence, this p squared, of course, is equal to p. In general, it is not. So this kind of relation actually extends the natural partial order on idempotence. And this, I point this out because, again, one easily shows from the definition that our map phi, which is assumed to commute with this kind of product, preserves these relations really nicely. But before we go to that, there is a slight snag, let's say, regarding these k potents, which complicates things with respect to the idempotent case. So, of course, any idempotent in any algebra over any field is, in any matrix algebra, is diagonalizable. This is not the case for k potents in general. So we get that all k potents are diagonalizable if and only if the characteristic of the field does not divide k minus 1. So if this condition is true, so if the characteristic divides k minus 1, we can have some kinds of idempotent, some kinds of k potents which are not diagonalizable. For example, this one. This is an example, and this phenomenon complicated our proofs a bit in contrast to the idempotent case. But again, it is not of the level way beyond linear algebra. But still, okay. So another kind of thing which appeared in the proof, which is interesting, is some kind of a generalization of that proposition we saw earlier with the left-nested iterated Jordan product. So we had a set which is assumed to behave something like an ideal, again without linearity, so it's not assumed to be a subspace, but it is assumed to be closed under this kind of a multiplication operation. So now one of the factors has to have this kth power, and J is so assumed to be closed under this kind of operation. Then we get, again, a kind of a simplicity result in the sense that J has to be trivial, is either 0 or everything. This was again used to show that any non-trivial example of a map which preserves this kind of product cannot annihilate any non-zero matrix. And we also get an analogous result for that lemma we saw earlier. So if phi is an arbitrary map between two different matrix algebras which preserve this kind of a product, then we have these kinds of properties. So we immediately see that phi preserves k plus 1 powers, k plus first powers, and then in particular phi preserves k plus 1 potents. So if we have this map with k, then it is naturally the k plus 1 potents are natural objects which play the role of idempotents before, and we have all the same preservation relations. So phi preserves the standard quasi-order on them. Also, if with these assumptions, if phi is non-zero map but maps 0 to 0, then one easily sees that it preserves orthogonality, that it increases rank, and then that it preserves rank, and then the restriction is orthoadditive, which means that if two k plus 1 potents are orthogonal, then phi of sum is equal to sum of phis, and the extension of this results to linear combinations of such k plus 1 potents. So again, the proofs of this are similar to the idempotent case, but are strictly more complicated because of that non-diagonalizability phenomenon. So we had to do some kind of calculations differently. And okay, this is basically it. There is also a natural question for which we reserve for future work, and we don't know the answer to yet. So what about maps which preserve our products? This kind of a mixture down power product, but with different exponents. So it is unlike in the case when one of the exponents is 1, when you look at the set of all such matrices, when A and B go over all matrices, it is not entirely equal whether this set is even the entire matrix algebra. So when one of them is when one of the exponents is 1, of course one can put the identity matrix, we obtain the entire matrix algebra. So if the set of all matrices encompassing this form is not the entire matrix algebra, then of course we cannot expect automatic additivity or that nice dichotomy. But actually, in some cases, we do know that it is not everything. But the real question is for which choices of K and L can we obtain this dichotomy results and characterizations of such maps, and this is a work in progress. So yeah, that's basically it. Thank you.
Thank you so much for the presentation and the very clear talk. I enjoyed a lot. So I should ask to the audience, are there any questions or remarks, or would you like to make any comment?
Yeah.
I have a question.
Yep.
So it seems like all the results that you presented are positive in their nature. Like the conclusion is that usually multiplicativity implies additivity.
Yes.
Is there any counterexample apart from the
Yes.
constant case?
There are lots of counterexamples because those results were had the bijectivity assumption or injectivity assumption or something like that. So usually for generic map you don't get this.
I see.
So they're like these kind of degenerate examples.
And under the bijectivity assumption, do you expect it to be always additive?
No. Again, no. I wouldn't say it is, but I don't know off the top of my head some example. But again, I would say that it is not additive in general.
Any other question? Well, I have just few comments or maybe open questions or ideas in my mind. This is quite natural related to, I mean, this, especially the final part of your talk is especially related to triple products and somehow it could be related to preservers of triple products on certain more general structures like Cartan factors, G-star triples, especially because symmetric operators can be regarded as a special kind of Cartan factor. And we have studied similar problems, preservation of triple products. Actually, Friedman and Hakeda did in the 80s quite interesting study on bijections, preserving quadratic products. I mean, something related to what you call BAB. This is quite interesting from another point of view in mathematics and also in physics concerning these kind of questions. And I also have a small comment. I don't know if you are aware of a kind of reciprocal to the famous Gleason-Kahanay-Szelasco theorem.
Mm-hmm.
In that theorem, in the classical Gleason-Kahanay-Szelasco theorem, as when a linear mapping is actually a homomorphism. It preserves products, is multiplicative.
Yes.
Okay, but what about relaxing linearity, as you are trying to do, by assuming, for example, preservation of being multiplicative plus being a spectral value? There is a very nice study in the setting of C-star algebras and von Neumann algebras. It was completely solved by authors like Brits, Touré, and Schultz quite recently. And we also extended that to the case of JV star algebras and Jordan-Banach algebras complex in the complex setting always. But I think it could be related to your results somehow. I mean, in those cases, we are not actually reduced to I mean, semi-prime or prime or simple objects. You can consider general phenomenon algebras, and I mean, it could be the structure could be a bit more complicated than matrices. But anyway, this is quite very natural related to this kind of problems studying automatic linearity, if you allow me to say that,
Yes.
maps preserving products. And in all those cases, for example, we required the mapping to be multiplicative plus being a spectral valued. I mean,
Preserving.
yes,
Yeah.
well, we only consider for the moment we could only solve the problem in the case that I mean you have a functional. It takes values in the base field. You
Okay.
know,
Yeah.
so but this could be very interesting, and I mean the overlapping with your results. I enjoy it a lot.
So
Uh,
my co-author Ilja, Ilja Gogić, his area of research primary is actually C-star algebras. So probably he could contribute more than I basically work mostly with matrices. But yes, so usually for other, we did think about other settings for this. Of course, this presence of many idempotents was essential for proving these results. So maybe von Neumann algebras could be used in this sense because they have, I think, many idempotents inside.
yeah.
So it could be a natural setting to look at, to try to adapt a similar proof or maybe a different one.
Yes, I could even email you some of the results.
Yeah, go ahead. Yeah, thank you.
Okay. That's all from my side. Any other question or comment? So if that is not the case, let me congratulate you once again for the clear presentation, interesting results. It was a very nice complement to the previous talk by Ilja Gogić. So thank you so much. That's all for today. I hope to find you in this Monday European seminars, and so see you next week.
Yeah, see you.
Bye.
Bye.